Okay, let's pick one more Boolean function to do. What function am I thinking of?
XOR is always good.
Let's do XOR. So what does XOR mean? Remind me.
Okay, XOR is exclusive OR, which means it's true if A is true or B is true, but not if they're both true. So it has elements of both OR and in it.
Right.
And I think of XOR usually when I'm like playing with light switches in my house. If I have a light that's activated by two different light switches, it's usually an XOR function. If one is up, the light's on. If the other one's up, the light's on. But if they're both up, the light goes back off.
Right. The other thing, when I think of XOR, is when people say OR. Most of the time when people say OR, when they're talking, they mean XOR.
Really?
Yeah, so a lot of times when people say OR in English, they really mean XOR. They say, well, do you want to go to the movies or do you want to go swimming? Do you want to eat chicken or do you want to eat fish? And really they're saying either or.
I see. You want one or the other, but you can't have chicken and fish or go swimming and the movies.
No, those things are not possible to do together.
Got it. Okay.
All right. So how would you do XOR? We still have our two attributes A and B.
OR, because it's a lot like OR.
So what would you want to do?
Okay, so to do XOR, we can split on A.
Okay.
And there's a true branch and a false branch. And what happened with and OR at this point is there was at least one branch where we actually knew the answer at this point. But I don't think that's true
right.
here. So if A is true, the output might be true or false. It depends on B. And if A is false, the output might be false or true. It depends on B. So
that's exactly right. So I guess in both cases, we still have to split on B.
Okay. All right. So but now it should be relatively easy in the sense that there's a separate leaf for all possible inputs. And so we can just write the XOR function on the bottom. So if A and B are both true, then the output is false because it's exclusive. If A is true and B is false, then it should be true because A is true. If A is false and B is true, then it should be true because B is true. And if A and B are both false, then it should be false.
That's right. And by the way, if you were to think about it a little while, it would probably occur to you that this tree is just another representation of the full truth table.
Ah, very nice.
And in fact, if we wanted to do OR again, we could say, well, I was very smart last time, but I could actually write OR like this. And then just fill out the values at the bottom. If A is true and B is true, then yes. If A is true and B is false, then yes. If A is false and B is true, then yes. If A is false and B is false, then no. And this is a perfectly legitimate decision tree to represent OR because it basically is just another simple representation of the truth table. But as we pointed out when we did it last time, it's more of a decision tree than we actually need.
I can see that.
Because in particular, we don't actually need this. All right, so this little difference here between writing out the entire truth table on the left, as we did for XOR, and not having to write out the entire decision tree on the right for OR, actually is going to turn out to matter when we try to do things either more complicated or with more attributes than we did for these simple AND, OR, and XOR. Would you like to see?
Yeah, that sounds really cool.
Beautiful.